Okay, so for part 3 here of 7-3 notes, we just have a few more examples to wrap up here. So a few more of these examples, make sure we're comfortable with, and we'll finish this out. So the idea with question example 5 here, right, is you've got this wheel that's being spun around the pivot point around this axle here, and we want to find out what the initial angular acceleration of the disk is once this pin over here is removed, right? So if I remove this pin, obviously the disk is going to rotate. They're showing us a couple different forces acting on the disk here, and they want us to find the angular acceleration of that disk, right? So that's what we're looking. So then to find our angular acceleration, right, we need the net torque. So the same equation we were working with for the most part, right, in the last few parts of the video here as well, right? So the net torque equals the moment of inertia times the angular acceleration. And so this problem hopefully wouldn't be one that's too bad to then find the net torque. The tricky part is going to be finding the moment of inertia, right, for this device that's being pivoted around the axle here, right? So the net torque, well, if I look at this object, there's only a couple things contributing to the torque. So let's go ahead and start with that part, right? So if this is the pivot point, then I'm not worried about the force acting at the axle, right? Since that's the pivot point, that means there's not going to be any torque produced by that force. So there's only two forces that are going to generate any torque. And with respect to this pivot point, each of those two forces is going to cause it to rotate, in this case counterclockwise, around the circle, right? So each of those two torques is actually going to work together as they cause this rotation. So the torque of this tension here, right, tension times radius, and then plus the torque caused by the force of gravity here, so the force of gravity times that radius. So I'll call this R1, I'll call this R2, where the radius is the distance away from the pivot point, right? So again, in this case, actually pretty easy to find our net torque, right? Our net torque is just going to be the tension, which is 100, times my 0.025 meters, plus my force of gravity, so my 5 times 9.8 times 0.025 meters, right? So just calculating that total torque shouldn't be too much of an issue then for us, right? No big deal if we go through and find that. So the net torque in this case ends up equaling about 3.725 newtons per meter, right? So that is our net torque for this particular example. I don't know why I'm boxing that in, because we're not done with this by any means, right? So that's the net torque. So then finding the moment of inertia is a little bit trickier, although hopefully at this point not too bad. The moment of inertia is not just going to be my 1/3 or my 1/2, in this case mr squared, right? And the reason it's not is because it's not being pivoted around the center of the disk there. So instead what we have to do is we have to use our parallel axis theorem, which goes back to what we saw in the end of the last chapter, right? But the parallel axis theorem says the moment of inertia for an object pivoted somewhere other than its center of rotation is going to be the moment of inertia about the center of mass, which is 1/2 mr squared, plus m times d squared, right? So again, my moment of inertia is 1/2 mr squared plus m times that distance squared, right? And in that case, the distance away would be that 0.25 or 0.025 meters squared, right? So all I have to do then is use the parallel axis theorem for this one, and it's actually not too bad, right? So my moment of inertia for the disk equals 1/2 the mass of the disk, which is 5, the radius of the disk, which is 0.05 squared, plus again the mass of the disk times 0.025 squared, right? So there's my total moment of inertia, right? So 0.009375 kilograms times meters squared, right? So that is my moment of inertia. So I've got that taken care of, no big deal. And then finding my net acceleration, finding my angular acceleration, right? Just bringing all of those facts together. So I've got my net torque, I've got my moment of inertia. So then torque equals the moment of inertia times the angular acceleration. So then 3.725 equals 0.009375 times my angular acceleration. Right, so then just solving from here to find my angular acceleration, and obviously it's going to be a fairly high number based on these two measurements, but we should get the angular acceleration to be about 397 radians per second. and you'll have to forgive the noises in the background. It is laundry day here in the Dorsch household, so you may hear some of those noises going on in the background. But anyway, that finishes out example 5 here, so picking up with example 6 and 7. Okay, so example 6 here is a good example for how to incorporate a system of equations when we have both linear and angular measurements, right? So they say we've got the wheel, they give us the measurements here of the wheel being R and M, and then they say we have a mass that's suspended from that. So you have a string that's hanging down and a mass suspended from that wheel. And then when the wheel is released, the object accelerates downward. We know that's going to happen. The cord unwraps the wheel rotates with an angular acceleration. Right? Find expressions for the angular acceleration, the translational acceleration, and the tension. So obviously all of our answers are going to be in terms of kind of the measurements they give us. So M, R, and this lowercase m as well. But we do want to try and find measurements then for each of those values. And so the big concept with this question is we set up a system of equations much like we would have ordinarily done, right, if this was a pulley problem. So if this was a pulley problem and I had masses on either side of the pulley, then the way that I would approach this problem would be I'd find the net force on this mass and then the net force on the other mass and go from there. Right? So I'll still do that. I'll call this mass 1 just to distinguish that, right? And I would still start this problem by finding the net force on that first mass. So if I think about this, once I release the wheel, I know the force of gravity on that first object is going to be pulling downward. I know the tension is going to be pulling upward. So my net force on that first object is going to be the force of gravity pulling down minus the tension pulling upward. Right? So this is my equation. So breaking that up, this would be MA equals mg minus tension. So in this case, it's got an equation set up. Both those m's are allowed. However, I do have two variables here that I'm looking to solve for, right? I have both the linear, the tangential acceleration, and the tension. So at some point I'm going to have to do something to substitute one of those out of the equation. Right? So this is my first equation. So then setting up my second equation, right? I don't have another object, so instead I'm focusing on the net torque for the wheel. Right? So the net torque for the wheel, well, the only force that's producing any torque on this wheel is going to be that tension as it pulls down on the wheel, right, which would cause it to rotate, in this case, clockwise. So the tension there, acting a certain radius away, is going to be the only torque-producing agent for this. So the net torque I know equals my moment of inertia times alpha, right, and the only force producing any torque is that tension, and it's acting the full radius away, right, and the tension is acting perpendicular to the radius, so I don't need any sine component. Right, so I set up this as my second equation. Right, so now I've got two equations. I've got the tension times the radius, and I'll go ahead and make this a capital R, since that's what they defined it as. And then it equals my moment of inertia times alpha, and then I have this equation over here. So I'm close to what I need, right? I do have two equations, and both equations do incorporate the variable t. The only problem is we have, in this equation, we have the linear acceleration, and in this equation we have the angular acceleration. So the question is, how can I tie both of these equations together? And the answer to that is my linear acceleration equals my radius times my angular acceleration, right? This is something we know going back a few chapters. So if I take this and plug that in for my acceleration, now I have mass times my radius times my angular acceleration, and again I should use a capital R for that, equals my mass times gravity minus tension. But then in this equation over here, I know that tension equals my moment of inertia times alpha divided by the radius, so I can substitute that value in down here, right, and I can bring all of these together into a single equation. Right, so obviously incorporating all of this in together, I have my mass times my radius times alpha. I do actually need to be careful, right? Both of these masses are the lowercase m because they're representing the mass of the hanging object and not the mass of the disk. Right, so keep that in mind as we're doing this. Same thing with that one. And then the tension, right, so the moment of inertia times alpha divided by r. So the good news about this equation, if I look at it, even though we do have a little bit of mess to clean up, everything is in terms of variables that we're allowed to use, with the exception being alpha. So I can try and solve this equation now for alpha. Right, so at this point it's just a little bit of algebra, right, to clean it all up. So add this whole expression over the other side. I have mr alpha plus the moment of inertia alpha over the radius equals mass times gravity. Right, so I've got that set up and ready to roll. And then all I have to do is factor out my alpha, right? So moment of inertia, or excuse me, my mass times my radius plus my moment of inertia over my radius, and then equals mg. And at this point, you could do any number of algebraic things to clean it up, right? If you wanted to get a common denominator here, you absolutely could. You could make this mr squared over r, and then that way when I divide both sides by this whole thing, I'm dividing it by the single fraction, right? Mr squared plus I all over r. So that definitely is something I can do. I can substitute that in instead, and it makes it a little bit cleaner to solve for alpha, right? So my angular acceleration, my alpha, would be my mass times gravity, and then dividing by this fraction, so multiplying by the reciprocal of that, right? So I'd be multiplying the top by r, and then I'd be dividing the bottom by mr squared plus I. So my moment of inertia, or excuse me, my angular acceleration equals mgr over mr squared plus I. And in this case, that's as far as we need to take it. That is my answer for the angular acceleration. So then to find the tangential acceleration, right, would just be a matter of multiplying this whole thing by one more r. So it's literally the exact same equation with the exception of mgr squared over mr squared plus I, right? That's it. That's it. But anyway, so I've got that. I will leave it to you guys to go ahead and solve for the tension then by plugging this back into either one of the equations up here, right? So you could plug in your angular acceleration up here and then solve for tension, or you could plug in your linear acceleration here and solve for tension as well. But it's not a terribly difficult task. It's just doing some more algebra. So I will leave that to you guys if you want to go ahead and finish this out and solving for the tension. But it shouldn't be too bad. So then finally, example 7, which is basically the same type of question as the one we just worked. So I will help you set it up, but I may not quite finish it in this part of the video, and I will just trust that you guys can finish it on your own if you need to. But anyway, I will help you set it up, and we can go around from there, right? So we've got our pulley. We've got a 2 kilogram bucket that is attached to that massless string, and it's wrapped around this 1 kilogram 4 centimeter diameter pulley. So basically the same setup I had last time. I've got my 2 kilogram bucket, and then I've got my mass of the pulley, which they gave me here. It does tell us it's a cylinder, which is important because I know the moment of inertia for a cylinder, right, for a disk is 1/2 mr squared. So that does give me some information since they give me that. But anyway, the bucket's released from rest 1 meter above the floor. How long does it take to reach the floor? So ultimately what this does again is it ties in linear kinematics with angular motion as well. It's asking me the time that it takes to reach the floor, right? So how long does it take to reach the floor? Well, if I think about linear kinematics, I know that the height, so the change in y, if you will, would be 1 meter. I know the initial velocity would be 0 because the system's starting at rest. And then if I could find the tangential or the linear acceleration, doing this would be just a simple matter of kinematics. So once again, this question becomes just simply setting up a system of equations that will allow me to find the tangential acceleration. And so as soon as I realize that, this becomes just a matter of basically the same 2 equations I set up last time. The net force on my mass, right, the linear force acting on my mass, would be the force of gravity minus tension, right, which we can set up that equation, mass 1 times acceleration equals mass 1 times gravity minus the tension. The problem is I don't know either the acceleration or the tension, so I get stuck. So then I set up my net torque, right, equals the moment of inertia times alpha. My net torque is tension times radius, equals the moment of inertia, which for again a cylinder would be 1/2 mr squared times the angular acceleration. So one of those radii I can actually cancel out, and then I can solve for my angular acceleration. Just like we saw in the last problem, the key concept here is the tangential acceleration relates to the angular acceleration by tangential equals r times alpha. So if I substitute that in, right, if I substitute in that value, I actually now have a system of equations that are in terms of the same 2 variables, both in terms of t and alpha. And so again, I will leave that to you guys to solve it the rest of the way from here, but it shouldn't be a terribly difficult problem, right, as soon as you can establish this, as soon as you can set this up. So make sure you do feel comfortable solving this type of problem. If you do need further assistance on this, obviously just come let me know and I can help you out with it. There are several homework examples like this as well. But anyway, that wraps up then section 3 of chapter 7, so just one more section after this, and I'll probably have you guys do the quiz before doing that final section.